Hi, apologies for being gone. I got pulled for something, so this shouldn't be too bad to follow along in a video. So just have your notes out, ready to go. We're going to be on page 17 in a minute. So if you want to head to page 17, your notes, and pause and then get to that, that would be great. All right, so let's start off with equilibrium. So we finished off Tuesday talking about Monday, talking about how some reactions can go backwards and forwards, not all of them. So, like fire, for example, can't. But some reactions can go from A to B and turn into C and D, and then C and D will run into each other and turn back into A or B. And eventually, the change is such that A and B is turning into C and D at the exact same speed that C and D is turning back into A and B. So it looks like we're not making any more. Which we aren't, but the reactions are still going backwards and forwards, where you're making the same going each direction. So that's what we call equilibrium. The rate of the forward is equal to the rate of the backward reaction. So you can actually mess up a reaction though once it's in equilibrium. So you imagine it kind of settling out, and then if you go over and you make a big change to the beaker that's holding this reaction, is going to do something because reactions want to be at equilibrium. I mean, just based on the physics, it's going to move towards balance where it's going to go in the same direction at the same speed. So on page 17, we're going to talk about shifting the equilibrium. So the question is if I'm in equilibrium, imagine that this is on like a seesaw. Okay, so the seesaw point is the double arrow, and on the left side we have some reactants, and on the right side we have products, but really that doesn't really matter because it's going back and forth anyways. So we have now reached equilibrium. We are good. Everything is, the rate's going backwards and forwards the same, nothing matters. So we start off by adding more N2. So imagine on your seesaw we're adding more N2 onto the left side. Well, if you're on a seesaw and you're already balanced, that's going to make it go, whoops, this is going to be kind of weird. It's backwards on my screen. You're going to want to go down to the left. Now, to fix that, we need to think about what do we have to add more to the which side to make it go back to being a balanced seesaw. So what's going to happen is equilibrium wants to push the reactants back to the products. We're going to make some more products. And so if we do that, that's going to make the right side more heavy, and then we're going to then be balanced. So I think of it as is, how are we going to fix that seesaw to make sure that it is balanced? Okay, so let's try another one. What if we add more H2? Well, H2 is again a reactant, so it's going to make the left side more heavy. So my question is, where is the shift in equilibrium? Well, it's going to push things to the right in order to fix it. So when I ask you the equilibrium shift, my question is, again, is how do we fix the change that disturbed equilibrium? Okay, I don't need to know that we added more reactant. I need to know how is equilibrium going to fix it. Okay, what if we take away N2? Well, if you remove something from a seesaw, it gets lighter. So if you remove N2, the right side is going to get heavier. Okay, and so to fix that, again, if the right side's too heavy, we need to then shift things back to the left side. So if this side becomes heavier, then we're going to then this side becomes lighter and goes up too high, we then got to push stuff back to balance it out. Okay, what if we remove H2? Same thing. We're removing a reactant, which means we want to go towards it to fix, we want it to be in balance. So that's all the reactant side. If we add more NH3, it's going to make the right side heavier. So the right side is now heavier. Okay, the right side is now heavier. So now we need to, again, push it back to the left in order to balance it out. If we remove NH3, it's going to make the right side lighter. So it's going to make the seesaw go up. And so if we remove NH3, the reaction is going to compensate by adding more, by turning the reactants into NH3 products. So that's how you deal with reactants and products. Basically, if you add reactants to one side, they're going to turn it into products. It's like having extra reactant. If you remove reactants, then the equilibrium's like, whoa, where'd all these reactants go? We better make more to fix it. So the equilibrium shift is basically going to do the opposite. Adding more reactant makes it go to products. Adding more products makes it go to reactants. Removing reactants makes it goes to reactants to fix it. And then removing products makes it goes to products in order to fix it. Okay, kind of pause for a second, think about that. I know it's kind of a tricky concept. The only other thing is heat. Well, treat heat like a reactant or product. So if we have heat is, and you should know this, what kind of heat reaction is this when heat is over here? This is a endothermic reaction, so heat is going in. So if you add heat, again, it's like you add a reactant and you make it go down. We want it to go back up. So heat's actually going to push it more to the right because you added more reactant. And if you removed heat, again, it's like removing a reactant, and that's going to make it go back to the other way. So removing heat will then make it move back towards reactants in order to facilitate that. Okay, ignore pressure. That one's kind of not what we need to talk about. But there is two more things we can look at. What if we add a catalyst? So remember, catalyst makes reactions faster. So remember elephant toothpaste, we added a catalyst, and that greatly sped up the reaction, and now it went very fast. Well, the thing about making it faster is it doesn't make either side more faster. It just makes both sides go faster. And so even if you have 10 speed on the left and 10 speed on the right, if you double it, it's still 20 and 20. It's not going to change it. So when you add a catalyst, you aren't really changing the equilibrium. So it's going to do nothing. It's not going to go left or right because adding catalyst just makes you get to equilibrium faster, not change where the equilibrium is. This is going to be the same reason for stirring it harder. So stirring causes it to have more collisions. So if you stir, you stir, you stir, the chemicals are going to run into each other more. So stirring will then also make it get to equilibrium faster, but it's not going to make more products and more reactants form. It's not going to try and fix it. So if it's not removing or adding reactants and products, which includes heat, then basically it's probably not going to do anything to that. So take a look at this. See what you think of it. I have a couple practice problems on the next page, which I think is 18. So flip the page, try the first 5 on your own, and then check with this video. And then try the second 5 on your own, check with the video. And then you'll finally do the Kia and make sure all your work has been done for the last few weeks. So let's take a look at the question set. So here's a new reaction. 2SO3 plus heat turns into 2SO2 plus O2. Technically, this should have a double arrow. That's an error. But figure out what would happen if you did all of these things. So pause the video here, and then I will show you the answers in a bit. So don't cheat. Try it on your own, and then check. All right, so now you unpaused. Again, trying it on your own. Let's see what the answers are. So increasing on temperature means you have more reactants, so you're going to push it to the right towards products. If you remove O2, the O2 is going to go down, so you're going to want to push it back to the right to fill it back up. If you shake the reaction, nothing's going to happen. If you add more SO3, you're going to then push this down with more products, so we have to then turn that into, you're going to push this down by having more reactants. So we need to push that more to the right to even it out. And then again, adding a catalyst doesn't do anything. Okay, so try question set 2. Again, kind of pause the video. You can unpause in a few seconds and see how you do. All right, so you should have tried this one on your own, see if you got it. So this one we have add more N2O4. That's going to push it to the left because you made the right side much heavier. If you remove NO2, we need to compensate by filling it back up. So we're going to go from the right to the left to redo the reactant. Adding a catalyst again doesn't do anything. Increasing temperature makes the right side more heavy. So again, we're going to push it to the left to balance it out. And then stirring the reaction, again, does nothing. So it's a little bit of a challenging concept. You need to think about equilibrium and balance and how if you change one side, it's going to want to go to the other side to try and fix it somehow. So things to work on, they're the Kia that looks at equilibrium and Le Chatelier's principle. He's the guy who came up with this. If you mess it up, it tries to fix it. You should make sure you do the equilibrium lab and turn that in. There were a few post-lab questions, but your graph should be done and all that. And finally, you should have pages 3 through 18 complete. So flip through all those. Don't wait till the day before this whole pack is due because it's a big one. And see if you have those pages done. And then tomorrow we will be looking at our titration, a very complicated lab. So if you want to start reading that lab work, you could if you have some extra time today, but you should have a lot to work on with the Kia and all of our old lab activities. So I will see you Wednesday. Be nice to the sub. Thank you very much.